Thank you all for joining us tonight. My name is Arturius Reyes. I'm the president-elect for the New York chapter. And I'd like to welcome you all to the past president and sponsorship recognition night tonight. Tonight we've got a pretty packed agenda, so I will try and be as quickly and efficient as possible. First, I'd like to call up our membership promotion chair, Stanley Funk. Stanley.
Thank you. What we're going to do this evening is we're going to just give a shout out of recognition to those of you who are a part of organizations that have been sponsoring our local New York chapter of ASHRAE. This is a very important part of what we do here in New York, but so those of you know that these monies that come into this chapter, a portion of that goes to national ASHRAE as well. And that is where a lot of the research is funded. The studies that come out of ASHRAE, a lot of that comes because of the what you are doing in sponsoring our local chapter here. So as we move forward, I do have a list here that we're going to be following. When we call out your name, if there is somebody from your organization that is here, please do come forward. We have a certificate for you as well as a coin based upon the level of sponsorship that you have. So we'll be recognizing the leaders first. Leaders with us this evening, CDE Air Conditioning Company, CE Applied, Con Edison, SRS Enterprises. And if you just come on forward so that we can pass these out to you, just speak to Arturius here and he will give you the appropriate information. And one of the coins, Arturius, the red pouches are for our leaders. So just give one of those coins to each as well as the certificate. Okay, and we have SRS and also WSP. Okay, and then we move on to our partner level. The partner level supporters or sponsors of our organization are AKF Group, Belimo, Fulcrum Group, GA Fleet Associates, Goldman Copeland, JB&B, Mitsubishi Electric Cooling and Heating, Siska Hennessy Group, Tech Systems, Technical Air, Train is standing right behind me.
I'm right here.
Okay.
Tech Systems.
Tech Systems.
Yeah, I'll give that to John after.
Excellent.
Thank you.
And Train is the last one. So that is that rounds out our partner group. So thank you for those of you who are supporting or sponsoring our ASHRAE local New York chapter at the partner level. And there's going to be a number at the supporter plus level. And these, let me just call out the names again. If you're here, please come forward. And this will be in the order of, okay, ADS Engineers, Cerami and Associates, Chimney Design Solutions, Daikin Applied, Echo Care Corporation, Federal Pumps, IMI, Hydronic, Johnson Controls, LF Systems, MPN Boilers, National Air Filters, or National Air Filter Services, Rath Associates, Schneider Electric, Siemens Building Technologies, Skyline Engineering, Thermal Systems Associates, Victaulic, Wales Derby Incorporated, and Wallace Ennis. Thank you all for being the sponsors of our local New York chapter. And here's to a fantastic 21-22 year, and we look forward to your ongoing sponsorship into the future. Not at all.
Thank you, sir. Thank you. And now we will transition to our current president, Ben, online for the past president's introduction.
Thank you, Artorius. Greg, can you hear me? Greg?
Yes, we can. Yes, we can.
Okay, great. Good evening, ASHRAE, New York. So my name is Ben Rodney, president for 2021-22. I sincerely apologize I could not be there tonight, but I plan to see everybody on Friday at the annual gala. So really looking forward to seeing everyone there. Tonight we're celebrating our 110th year as a chapter, which, if you think about it, is quite astounding. The chapter was started in 1911, and from 1911 to 1917, our chapter was known as ASHVE, or the American Society of Heating and Ventilation Engineers. And then in 1917, the New York chapter of ASHRAE, or American Society of Refrigerating Engineers, was formed. And we had two organizations here in New York City, each with its own president. Then in 1958, the two organizations merged into what we have today, ASHRAE, and our chapter moved back to a single president. And if you visit our website, you can find a complete list of past presidents as well as our chapter history up to 2011. So it has been an honor to serve as the president of our chapter this past year, and there's a special privilege and a sense of duty to the chapter that goes along with this role. But tonight is our opportunity to honor all of our past presidents, and we have a number in attendance tonight. And so I would really, I would encourage all of the past presidents in the room, and Artorius, I might need your help with this, but for all of the past presidents in the room to come forward to the left of the podium, and then we'll begin our recognition.
And to the left, this side. Oh. Ben, my left or their left?
Oh, you're right, Artorius. Sorry.
Sorry, to the right, everybody. Sorry, to my right.
Sorry, Greg said that was the best spot. Sorry. I already see one or two people I might not have on the list here. So we tried to organize it by everybody that was going to be there. So we're going to announce, if everybody could, I'm going to announce some names, and if you could just raise your hand upon recognition. Oh, there we go, Greg. Thank you. So that everybody in the room who may not know who you are can know who all have served our chapter. So I'll go through first. So Joseph Lee, 1987, 1988. Joe Azera, 88, 89. Anthony DeFiglia, 94, 95. Bill Ryan, 96, 97. Gene Geyer, 2001, 2002. Kevin Galen, 2009, 2010. Ramez Fifi, 2013, 2014. Charlie Marino, 2015, 2016. Jose Rodriguez, 2016, 2017. Frank Rivera, 2017, 2018. Anthony Montalto, 2018, 2019. Jinjin Huang, 2019, 2020. And Tony Sang, 2020, 2021. And I can't see everyone. I may have missed a couple people. Maybe Jinjin or Artorius, if you could help us out.
Of course, last but not least, Monica Pearl, 2010 to 2011.
Al Nicholas, 92, 93, long time ago.
John Rice, 2003, 2004.
Oh, wonderful.
Chris McHugh, I believe it was 88, 89, or 89, 90. I can't remember. Kidding. It was 99. It was 99, 2000. That was it. Blends together. Old age.
Thank you. So, and I'm really ecstatic that we had even more show up than we had planned. So it's great to see everybody. Now we wanted to give a special recognition to our two previous past presidents, Jinjin and Tony, from the past 2 years. Do we get our photo? Great. So due to the pandemic, we've been unable to properly recognize their years of service as president and the years of service they've provided to ASHRAE New York. So Jinjin served in 2019, 2020, and provided some incredibly strong leadership, bringing a deep connection from the society and regional level to the president's role, along with an extensive technical and managerial background, which was critical for leading our chapter. She's been a great friend with over a decade of service to our chapter. And Tony served in 2020, 2021, and had the distinguished honor of being the first president unable to see his chapter in person for an entire year. So Tony has been dedicated to ASHRAE New York for many years, bringing immense creativity, passion, and ideas to the chapter. And his year as president was extremely difficult given the pandemic, but ASHRAE New York was able to excel and lead Region 1, ultimately winning the Golden Gavel Award for that chapter year. So we want to honor both Jinjin and Tony with these plaques to commemorate your service as president of ASHRAE New York. So Artorius, if you would be so kind to present the plaques to Tony and Jinjin. All right, and back to you, Artorius. Thank you, everyone. I'll see you at the gala.
Thank you, Ben. Greg, you want to readjust the camera or when you get a second? All right, moving on to some quick announcements. Upcoming events are YEA Professional Development. That is coming up on June 15th. Registration is on our website. Please check it out. It's going to be a great event. Ralph Kizin does our leadership training. He is a very, very good instructor for ASHRAE Society. And I'm very much looking forward to this event coming up. Next, we have the gala coming up on Friday, hoping to see you all there. We are not sold out. We're almost sold out. So please go online, get your tickets, and look forward to seeing everyone on Friday evening. Next one. And now to our distinguished lecturer, Mark, for our technical session for the night. Welcome.
Thank you. Really honored to be here on your last official meeting of the year, and President's Night shows a lot of history and a lot of involvement here. So, we okay? Okay, good. So I'm Mark Fly. I happen to work at AAON, but I'm also an ASHRAE Distinguished Lecturer. And the ASHRAE Distinguished Lecturer Program is part of society. It's brought to you by the Chapter Technology Transfer Committees, which is all the regional vice chairs for technology transfer. So all the program and technology transfer chairs from all your chapters report to regional vice chair, and all those people set on a committee at the society level. So, so please do get involved in ASHRAE. I see a huge amount of commitment in this chapter already, but as Jen can tell you, there's lots of other places to go and lots of other ways that you can be involved. So I've known Jen through my work at Society. So anyway, that's my ASHRAE advertisement. These are the learning objectives. I don't want to spend a lot of time on them because if you don't get this, I didn't do my job. So we're going to move on. So what I'm going to talk about is kind of the really practical side as much as I can of acoustic design. And, really the intent of acoustic design, and one of the things that I see sometimes gets lost in the noise, so to speak, of the design process, is what we're really trying to do is design comfortable spaces for people. And so a lot of the things that we deal with acoustics, and many things in our ASHRAE, or in our not just our ASHRAE, but in our work life and design, sometimes we get a little too caught up in the tools. And these are all just tools to help us better understand how to create better spaces for people. But sometimes those tools also can get in the way if you take them too seriously. So one of the things that I think is a big misconception is being too quiet can be as big a problem as too noisy. And so I'll tell you a quick little story on myself. So I really got into acoustics in 1990. I happened to go to work for a company, and they said, "Do you know anything about acoustics?" And I said, "Well, I'd been a consulting engineer, and I ran a certain vendor's acoustics program way back when they had punch cards." And I said, "Good, you're an acoustical engineer. The meter shows up next week." Had fun with that. So we were testing. I was a manufacturer. We were testing a piece of equipment. We tested the piece of equipment. Of course, it didn't pass. We did all kinds of things, spent all kinds of money, changed fans out, put insulation in, did modifications to the unit, finally got it to pass. The acoustical engineer came in to witness the test and said, "Yeah, you passed, but this project is on the approach to LAX, and I was really hoping that your units would be a little bit noisier to help mask some of the airplane sound going over." So so being, air conditioning noise is many times used for masking. So being too quiet, it's not just about getting it low, it's getting it low and appropriate. So, and that also means without the presence of tones and level variances, and we're going to talk a little bit about that. And one of the tools we use for that is NC and RC curves, and we'll talk some about that. So, what is really sound, and how do we hear it? Really, so we're talking about being not objectionable to people. We have to understand how people hear. So a lot of our tools and a lot of things that we've developed are about how people hear sound. If the tree falls in the woods, I don't care if it makes a noise or not if nobody hears it, from an acoustical design standpoint. So, sound or noise, when we say noise, we usually say it's a sound that causes a negative psychological reaction, but it's basically just pressure waves that are actually impacting someone's eardrum. And sound has certain characteristics, these tools that we use to design around. It has a frequency, it has a wavelength, which has a lot to do with the environment when you're calculating environments. And the wavelength is the speed of sound divided by the frequency. So, the first octave band, what we call the first octave band that centers around 63 hertz, that wavelength is 17 feet long. So, strange things happen in a 10 by 10 room when you got a 17-foot long pressure wave in it. It gets very difficult to manage. And then the other thing that we do is we measure all sound quantities, whether they be apples, oranges, bananas, whatever they are, in decibels. And that's part of what makes it so mysterious and what scares a lot of people off from acoustics. But it's really just simple algebra decibels are logarithms. They're just a measure to a reference. And the reason that we do decibels to measure sound is because the way people hear is on an exponential or logarithmic scale. We have an incredible dynamic range of frequency and an incredible dynamic range of volume. And it's not linear, and it closer matches a log scale. So we make all the measurements in a log scale type measurement. So decibels are 10 times that logarithmic ratio. So in acoustics, in HVAC acoustics especially, there are three basic types of measurements we talk about. We talk about sound pressure, what you're hearing, what this microphone is picking up, what these speakers are putting out is creating pressure waves in the room, root mean squared pressure waves that we're measuring that we can measure with a meter, and that is the end goal. That's what we want to control. Now, to make that sound, my voice or this speaker has to have a certain amount of power that goes into it. So from an acoustical consultant or acoustical engineer, they want to know how much power is being produced by this device. And then if you put that device in an environment, then you can calculate how much pressure is happening in that environment. So if I stand in a 3x3 closet next to you, I'm going to sound a lot louder speaking at the same volume as if I was in this room and turned the mic off. So the environment very much matters on sound pressure. It does not matter on sound power. It's how many watts it took to put it in there. And you'll notice that the references are 10 to the minus 12 pascals, 10 to the minus 12 watts. It's not a lot of energy. And then there's a sound intensity, which is really just a measurement tool. It's a watts per square meter that can be measured by taking two microphones and looking at how fast the sound arrives at one microphone as compared to the other one. And it's really not used for anything but as a way to measure things. So if we look at sound pressure, the threshold of hearing in the mid bands is generally thought to be about 0. The threshold of pain is somewhere around 130. I was telling a few people here last night, I was at the Eagles concert in Tulsa, Oklahoma. We weren't at the threshold of pain, but I'm pretty sure we were up at least in the 90s. So my hearing today may not be quite as good as it was yesterday. And we'll talk a little bit about that. So sound pressure is dependent on position and environment, how soft or absorptive or reverberant or hard is the room. It's going to make a big difference in the sound pressure. And to get this neutral sound, this non-objectionable sound, we use criteria. Criteria like dBA, NC, RC are all sound pressure criteria. They're weighting systems to put a single number on a whole bunch of frequencies of sound. Now, you see people put dBA and NC ratings on sound power. That's not really appropriate, but it's done. But really, it's a sound pressure. So, like I said, sound power is how much sound is generated. And the way the references are set up, the sound, if you could put your ear right at the very source of the sound, then the sound pressure and the sound power would get very, very close, be just about the same. So as you get closer to the source, the sound pressure goes up to equal the sound power, but the sound pressure will never be greater than the sound power in decibels. And like I said, sound intensity is really a flux, a pass through a surface. So what you use sound intensity for, if I had a little device here and I wanted to measure the sound coming out of it, I could make an imaginary box on it, measure the sound on each surfaces of that box, figure out how many watts per square meter is passing out of all those, sum all those together, and that would give me the power that's coming out of that device. And the promise of sound intensity is if I have steady state sound, like the construction across the street, coming into my box, if it comes in this side, it comes in as a negative. It goes out that side, it comes out as a positive. So it should cancel it out. That only works if it's steady state and you're not too close to it, and it's not too reflective, but it has some application. It is really the only way to field measure power being put out by a device. So, like I said, one of the things that scares everybody is all the math involved, because they are logarithmic values and because the way your ear hears. When we add decibels, we have to unlog them, add them together, and relog them. And as my high school algebra taught beat into me, logarithms are exponents. So you take 10 to the decibel divided by 10, you add them all together. And so if you have 100 decibels and 100 decibels and you turn both speakers on, it's not 200 decibels, it's 103. And they're within 2 to 4, then it's 2 dB more. If it's 5 to 9, we add 1 dB. And if it's more than 10 decibels apart, the loud guy wins. If it's more than 1 decibel apart, it's less than a half a decibel. We always round to full decibels. And we're going to talk about what our hearing sensitivity. No one can hear a half a decibel. I don't care how good you are. So if you chart that, that's kind of how it looks like when you add decibels together. As you see, we pass that half decibel line out at 10. So frequency is one of the components that we're concerned about, whether this is a high frequency or a low frequency type noise, or what components are in it. And it's the rate at which something vibrates back and forth. And in vibration, we talk about frequency. It's whether it be air or sheet metal drywall, your eardrum, all those things can have a frequency. Human hearing for a young adult is 20 hertz to 20,000 hertz. That's the academic definition of what people have. Everybody's different. And most of the sounds that we hear and most of the things we have in HVAC, hopefully, are broadband noises. And they're things that sound like rain or wind or hiss, or you can go buy these machines to help you go to sleep now that play bubbling brooks, and those kind of things are the soothing broadband noises. The things that are more annoying are the hum, the buzz, the whine, and then actually being at a rock concert last night, I got to feel the rumble. When you get at that really low frequency, that's when you can feel it in your chest, and you can feel that. So you get broadband sound, they go all over the place, and you got a mix of everything. But we kind of break that apart and start looking at the frequency components, because one of the things that we know is that higher frequencies are easy to attenuate and get rid of. Low frequencies are hard. So we want to know how much high, how much low. And to do that, we use octave band filters, and we've all heard about octave bands. And in HVAC acoustics, we typically number those. 63 is 1, 125 is 2, and each one of those is twice the other. It's not really 63, it's 62 and a half, but acousticians don't like decimal points, so we round everything off. So 63, 125, 250, 500, 1K, 2K, 4K, and then the 8th octave band, which I didn't have drawn, is 8K. These were developed in the 1920s and 30s when our scientific instruments were LRC circuits, resistors and capacitors, analog equipment. And so when you made a band pass filter to try to filter out a frequency, it had a skirt on it and it had a roll off on each side. Now today with modern digital meters, we can make that completely square, or so square that it doesn't matter to us anymore. But we still apply these because we don't want to change the definition of a decibel or a definition of an octave band. So even if you go out and buy a $50,000 high precision sound meter, it still puts the math in to round it off like the old analog meters did. And they have, like I said, they have a center frequency, and then they typically have a range in which they operate. So we're real concerned about, let's see, we're real concerned about this speech range, because, you know, part of this is we want to make sure one of the requirements in as we design spaces for people is that we want to talk to each other, and we want to be real concerned with that speech range. And that speech interference range is that center band. And the lowest bass to the highest soprano kind of fits in that center band. And you can kind of see the threshold of hearing isn't as sensitive at the really low frequencies. And this is kind of a classic chart. And then it usually cuts off at the higher frequencies. As you get older, as you go to more rock concerts, as you shoot pistols without hearing protection, as you do dumb things in life that we all do, you lose the high end frequency. As a matter of fact, we're going to find out how much we lose here in a minute. There we go. Now, for amplitude, like I said, no one can really hear half a decibel. If we're up in that speech range, that 250 range, if you're a trained acoustical engineer or a musician, then maybe you can hear better than 2 decibels. If you're really concentrating and you're listening, if they put you in a laboratory, they put headphones on and they play a sound and say, raise your hand when it changes, you might be able to hear 1 decibel. Maybe if you're really trained, most people can't. Usually it takes, you know, somewhere between 3 to 5 for somebody to say, yeah, that was a noise change. I definitely heard that change. And then most people think that 10 dB is about twice as loud. Now, if you do that math backwards, that's 100 times more power, 100 times more pressure that just made it twice as loud. So that's part of the reason we use decibels in that logarithmic scale, because we can hear very, very quiet sounds. We can hear very, very loud sounds. Okay. So, so the other thing that came out of a lot of research is that your ear doesn't look like those octave band filters. If you play 2 tones and they're closer together than what we call the critical band, then you'll only hear one of those tones. It will pick one of them and it'll dominate. So your ear is kind of a band pass filter. And that red line here that's kind of swooping up like this is the critical band. And you can see here's full octave band, 3rd octave band, 6th octave bands. So the math didn't quite match the biology, but it was closer. But you know, critical bands are very important when we start talking about tones, because if we have multiple tones that are close together, we can't hear them. As a matter of fact, this is exactly how MP3 music compression works. It takes all the frequencies in your music file and it records a tone for 1 tone, 1 number in each critical band, and then recombines that back together. And therefore you compress a whole lot of information into disk space. If you want me to analyze a noise file, don't take your iPhone and record an MP3 recording, because when I run it through the meter, I will see a series of spikes, because I'll just see the spikes that it recorded. So, but you know, they're real. Now, we got people that are real audiophiles and says vinyl sounds better than CDs. So maybe some people can hear it, you know, but that's the difference between the two. CDs are MP3 compressed. So one of the big problems in HVAC acoustics is tones, and this is actually a FFT plot, which is a 1 hertz by 1 hertz trace of a sound. Oops. Of a fan, and every fan has this spike at the number of blades times the RPM. So we call it the blade pass tone. So tones are a very important thing in HVAC acoustics because that's usually where you get in trouble. Those are the things that show up that annoy people. And so this is taking that same file and processing it with critical bands, and you kind of see the different bands are not exactly evenly spaced, but those, if you played this sound back versus the sound that I recorded before, most people could not tell the difference. And if you do it in third octave bands, it's not a bad representation for most things that have this frequency, this blade pass frequency, which is one of the things that happens in a lot of HVAC acoustics. So I always tell the people in my laboratory that everything in the world shakes at 125 hertz. That's kind of the range that most fan blade pass frequencies are. It also happens to be the buzz off electrical transformer, 60 hertz times 2, because it goes up and it goes down. All those things happen at about 125 hertz. So it's very common. So third octave bands do a pretty good analysis. When you go to full octave bands, those full 8 octave bands, then you lose some information, especially if that tone is very close to the boundary in between the two. And if you went to just a straight dBA, you don't get any information at all. So, okay, so I've been talking a lot about frequencies. We're gonna give everybody a hearing test. So part of it depends on the speakers, but so when I start it, you may not hear the low frequencies, don't worry about it. That's not where you lose your hearing. So pay attention to where you can no longer hear the sound. And we have a great range of ages in here, which is always good. So we're going to start out this number up here. That's the hertz. So I'm starting out at 31 hertz. Well, it does produce 31 hertz. Found a resonant in the speaker too. It sounds like it's getting louder because your ear is better. Okay, start paying attention to where you lose your hearing, anything past 8,000 hertz, probably. 10,000. Who can hear that? I can't. Still a few. Okay. That's 20,000 hertz. There is a little side band down here that a lot of people can hear. If you couldn't hear the one before, you probably can't hear this one. So, so if you looked around, who cut off? I cut off at about 12.5. So the rock concert last night didn't kill that. I could still hear that when I couldn't hear anything, or I couldn't hear anything past that. Anybody else before that? So if you notice the people that, when I started saying who can hear this, it's kind of the younger people in the crowd. Sorry for us old guys. As we age, we lose flexibility in lots of places, and our eardrums are one of them. so anyway, so let's talk about that was just kind of the fun part. Okay, so let's talk about some of these tools. So why do we design? you know, there's usually local, sometimes there's local codes. There's a code in New York City that says 50 dBA inside an open window is the criteria that any new building project has to meet. So a lot of those codes are enforced. Most of the building codes are outside noise criteria. There's not a law or a rule or administrative requirement for indoor noise most of the time, short of OSHA exposure, which is about 85 dBA. If you have an 8-hour exposure at 85 dBA, you should have hearing protection. That's what OSHA says. So, so most of them are in dBA. And the reason they're in dBA is that back in the day, you could go to Radio Shack when Radio Shack was still in business, and you could buy a very inexpensive dBA meter. And you could go, and any building official could go out and hold it in front of the window and says, it's over 50, you violated my code. That is after you turn the unit on and then off again, because in New York City, it's probably hard to record below 50 with an open window most of the time anyway. But nowadays we have all these, and you can get programs on here that are not bad, are pretty good, and are way more accurate than those old meters that we used to have. And you can get all kinds of things, but we're still enforcing dBA. When we go to indoor noise, then we kind of fall into the realm of ASHRAE. So ASHRAE has some recommendations. This thing keeps getting louder, seems like. Okay. Or I'm moving in front of the speaker. Maybe I ought to move back. Okay, that's better. So ASHRAE has come up with some recommendations for NC and RC levels. And so let's kind of talk about these criteria for indoor noise. You know, for outdoor noise, we talked about dBA. There's also a dBB scale and a C scale that were developed for very loud sounds, industrial sounds in industrial environments. But the way dBA works is it looks at each of these octave bands and you subtract off at the low frequencies, and actually you add on a little bit at the high frequencies, and then you add all those numbers together to come up with your dBA rating. So this is kind of how the curve looks. This curve will look different than the RC and NC curves because this is really just a filter put on that octave band data. When we look at RC and NC, those are two criteria that you see mostly in the United States. And this is one of the things I can tell about ASHRAE. I have met and known both Leo Baranek and Warren Blazer, the two guys that invented these two criteria. Leo was with BB&N, Bolt, Baranek, and Newman out of Cambridge, Massachusetts. They were the people that invented Milnet. No, Al Gore really didn't invent the internet. It was BB&N. And in 1957, almost 60 or 65 years ago, because that's the year I was born, Leo came up with this weighting curve, which are the red lines up there. And those are used very often, and they're applied in a tangential method, which means you plot the octave bands, whichever line it touches, that sets your value. There was a young engineer that worked for Leo at one point named Warren Blazer. Warren ended up moving out to the West Coast, starting his own firm, and he decided he didn't like Leo's criteria, and he came up with a criteria for RC, room criteria, and it averages 500 through 2K. It's straight 5 dB per octave. It's a little harder to apply because you have to average and then figure out where that hits on the line, but it gives you a little more information because if it's above, if it's high below that mid-range, then you call it rumbly. If it's high above that mid-range, you can call it hissy. So it gives you a little better characteristic to it. Both of them are used, and ASHRAE treats them exactly as the same criteria as far as numbers are concerned. So if I say I want an NC35 private office, it could be an RC35 or an NC35. I met both these guys in the ASHRAE 2.6 technical committee. When they both showed up, it was always a lot of fun to watch a couple of 70, 80-year-old guys scream at each other about whose criteria was better than the other guys. But and so this is ASHRAE's recommendation. So you have all this chart, and the ASHRAE handbook tells you that if you're in a private room in a hospital, it should be 25 to 30 NC or RC. So I got some of the older guys on the committee together one time, said, hey, could you point me to the deep ASHRAE scientific research that you guys all gave a lot of money to that set these numbers? Said, oh, heck no, we just went to the bar and we all decided on what they'd be. So many things in life are like that. So, so I'm going to play dBA, NC, and RC, and I've artificially taken white noise, which is just flat noise, and filtered it to match the NC, RC, and dBA curve. And that's what these next 3 sound files that you'll see are. So you can kind of choose for yourself whether you like NC, RC, or dBA. Well, that's dBA. That's Leo's NC. Now, obviously, these are loud. So you know, you could choose for yourself. I personally like RC if I had to play a sound to mask the traffic noise to fall asleep to, but everybody's a little different. It's RC or NC. I think dBA is really rumbly. It way discounts too much low frequency stuff, in my opinion. But like I said, everybody has their own opinion. See, we even got some sound effects today going on. So let's talk a little bit about how we measure sound. There are a bunch of standards. There's some ARI originally. I really need to change that slide. It's AHRI now. They've changed for basically telling you how to measure sound with a microphone in a room or in an outdoor environment. There's anechoic rooms. So in a laboratory environment, when we were trying to get pressure, there's 2 ways of doing it. One of them is called anechoic, where we have these big wedgie foam room. Anybody been in an anechoic room? They're really cool. You stay in them long enough, you can start hearing your own heartbeat and dead quiet, you know. But the problem is it's very difficult to make them anechoic at 63 and 125 hertz. Like I said, 63 hertz, the wavelength is 17 feet long. So I'd have to have 17-foot deep absorbers to be able to attenuate it. And usually that gets cost and practical inhibitive. So they do a really good job on things that don't make a lot of low frequency noise. Then there's the sound intensity. That was the one I talked about, where you could do kind of a field measurement. You can also do it in an anechoic room in a laboratory, and it looks at the rival speed of sound as it comes past 2 microphones and calculates a flux. And then the third one, the one that you see most often in the US for HVAC noise, if you're looking at equipment, whether it be compressors or fans or sound attenuators, all that testing is generally done in a reverberant room. Now, a reverberant room kind of works the opposite of an anechoic room. A reverberant room, ideally, if you have a room that echoes about 5 seconds, that's kind of the sweet spot. Then the sound pressure everywhere in that room, as long as you stay out of the corners and off the walls, approaches being the same everywhere in the room because it's just all bouncing around. Now that's assuming that it's steady noise, but like HVAC equipment's usually steady state. So if where the object is and where the microphone is doesn't matter anymore, And that's not entirely true because the microphone's on a boom and it actually sweeps around and gets a better average. But where the unit is doesn't matter anymore. Then I can calibrate that room with a reference. And so this little green fan sitting in the front, we call that a reference sound source. I always call it my $50 fan with $9,000 worth of calibration. And typically those are sent out and cross-calibrated to a master one that happens to live in Chicago every year, and so that everyone uses the same reference when they do their reverberant room testing. Reverberant room testing is very quick. You measure for about 32 seconds, and you can get a very accurate measurement of the low frequency sound and the high frequency sound. So you do all these measurements. How good's that data? Well, there's a certain amount of measurement instability. If I measure the same thing 2 or 3 times, I get a slightly different answer. So the standard deviation or the difference in sound power they're saying is 2 dB or less. Typically the standard deviation of those numbers are somewhere between 1 and 1.5 at the mid to high frequencies. The standard deviation at 63 Hertz is about 3. So if I measure that, if I take 3 measurements, it'll vary. It could vary as much as 3 dB. So if you remember your statistics, 2 standard deviations, 95% confidence. So we say that that the first band is ±6, all the other bands are ±2 in general. So there again, you're kind of in that realm of what people can hear if you remember that first chart. But it doesn't make a lot of sense to be arguing about 1/10 of a dB on anybody's spec because we can't measure it. And if you measure it 2 or 3 times, you'll get 2 or 3 different tenths you can argue about. So let's talk a little bit about fans and equipment. So this is a chart that I put together a long time ago, and it shows a whole bunch of different vibrations. And one of the things that you can do when you have a sound problem in a building, if you can have somebody come in and measure these frequencies and identify the offending frequency, then it gives you some idea of where it is. So if I've got something that has a lot of 1K and 2K noise, first thing that pops in my head is that's air noise. That's the diffuser. That is turning vanes. That's rumbling in the duct or something maybe. If I've got something really low frequency, that's probably driven off of vibration. Like I said, fan sound is fairly broadband, but that blade pass tone is usually the offending thing, and it's in that 100 to 500 Hertz band. Scroll and screw compressors get way up there. Centrifugal compressors get up there. So that's just kind of a troubleshooting thing. So sound and vibration are very much interdependent. So when you talk about transmission loss through the wall, me talking in this room, the person in the room next door hearing me, it's not that the sound is going through the wall. The sound is impacting the wall, shaking the wall at the same frequency as my voice, and then it's turning into a speaker on the other side of the wall and re-radiating that sound back. So it's a vibration problem instead of a sound problem. So that wall is a foot thick of concrete that's going to be very, very hard to vibrate. Very little sound is going to get through it. So sound can create vibration, and vibration can create sound. In all acoustical measurements, we have to assume all the paths. There's also lots of ways that we can get sound into a space. So this is very appropriate for New York City. I know you have lots of floor-by-floor air handlers, and if you have an air handler in this mechanical room, how it gets into this space, it can come through the wall is that vibration. It can come down the return duct and through the ceiling tile if it's a plenum return. It could come down the supply duct, actually break out the side of the supply duct, go out through the diffuser. There's many different ways that you can do that. If you have a rooftop piece of equipment, sometimes it's not the sound coming out of the diffuser. It may be the condenser fans that are actually wrapping around and going through the windows and through the roof structures. I don't know about New York. You guys still have a snow load, right? It's especially prevalent in the south and the west where there isn't a lot of snow. We've been building lighter and lighter and lighter gauge roofs, which vibrate easier and easier and easier and transmit more and more sound through them. So that's become a really big problem. There is a basic disconnect between acoustical engineers and mechanical engineers and the structural guys. The structural guys are required to do something like, their criteria is like 1/250th of the span. Well, that works great if the span's 20 feet. It might not work so hot when the span's 100 feet. It could have a lot of amplitude, a lot of vibration. And so that criteria doesn't match well with sound criteria. It doesn't fall in, but it transmits sound through it. We talked a little bit about that blade pass tone, and that blade pass tone occurs basically at the trailing edge of the fan. It puts out a tone, which is the number of blades times the RPM. And because that RPM is in minutes, we divide that by 60 to get it into seconds, to get it into hertz. And every fan puts out a blade pass tone. You may not be able to hear it. A lot of FC fans, you can't really hear the blade pass tone on them. If you have a vacuum cleaner, you can probably hear the blade pass tone on it. If you have a dust collector, you can probably hear the blade pass tone on it, you know. And then a lot of HVAC fans have something in between. There's also a fan law for acoustics, and this works pretty good. If you just need to have some idea, let's say I've got a fan and I want to get it quieter, maybe I can come up with a way of slowing that fan down. Is it going to get quieter? Yeah, it'll get quieter. And how much quieter will it get? Well, you can look at the sound power, and since decibels are all ratios, sound power is proportional to sound pressure. So if I can drop the power 10 dB, I drop the pressure in the room 10 dB. So the drop in that is proportional to 10 times the log of the ratio of the CFM plus 20 times the log of the ratio of the static pressure. Remember I said that logarithms are exponents, so 2 times the log, it looks kind of like pressure squared. Looks just like fan law. Now on outdoor equipment, on condensing units, in general, and there are a few exceptions, some high-speed centrifugals and screw compressors are the ones I'm thinking of. But in general, if you're looking at scroll compressors and a lot of packaged equipment, the condenser fans control the noise. They're making happy. You're welcome if they want to share them with you. I don't mind. But this is just gives you some idea of duct velocity. So if you're going for that performing arts studio or recording studio or really quiet space, then we're talking pretty low duct velocities to keep that noise down from being created in that ductwork. Okay, so I've got some real equipment. When you see the condensing unit, if you pay attention, you can hear some of that phasing that takes place. This is just a flooded fan. You should be able to hear a tone if you listen real close. I wouldn't talk over it. Those really aren't the same recording. They sound alike to me, but you know, if you've ever worked around screw compressors or centrifugals, you recognize that sound. So I'm just to wrap this up, I want to talk about, you know, I've been the acoustics guy at a manufacturer for since 1990 probably, and so you know when the customer's really mad, that's when they call me out. So you know, if I kind of list the things in my career that I've seen the most from, probably vibration induced sound is the biggest problem I find on a job. I always said I've solved more fan problems with a crescent wrench, taking the shipping blocks out of the piece of equipment and letting the isolators loose than anything else. Or it could be just being put on a roof support, because if you got a 1-inch spring on your piece of equipment and your roof deflects 2 inches because it's in that 200-foot span, then I always say the fan stands still and the roof does this. So, you know, the softest guy tends to move, so that inadequate. Probably the next thing is pure tones. Those pure tones, especially from fans, that condenser fan was pretty annoying. I didn't pick a good one to record. Next would probably be duct breakout and turbulence. You know, that's a really hard one to diagnose because everybody says, well, this piece of equipment's making too much noise, and when I turn it off, it all goes away. So does the air. So it's a hard one to sort out. And generally, like most things in engineering, it's a little bit of everything. Everybody's got a little piece of it. So, but if you can cure it by going in there and taking that rectangular duct, making it all round, it's very hard to flex a round duct, a circle. You got that hoop strength on it. I had a particular job where we had 40 by 12-inch duct running across the ceiling. They'd actually recess can lights into it. It was a really fun job. And we tore it all out and put 12-inch round duct everywhere, lots and lots of 12-inch round duct. And that solved the sound problem in that particular job. So it wasn't the equipment, it was really coming out of the ductwork. That flanking path I talked about, going around through this roof structure or through windows, and just in general forgetting, even though you meet the NC criteria and everything matches, if the customer's unhappy, you've lost, you know. And once you have a sound problem, people get very sensitized to that. And like you saw, different people heard different things when we played different tones. Some people, especially when they start paying attention, get very sensitized to those sounds. So as I talk to consulting engineers, friends of mine that I've worked with and come to know over the years, I always ask them, you know, how much of your work is before the fact and how much is forensic, fixing something in the back end? It's not uncommon for them to say somewhere in the neighborhood of 70 to 80% is forensic. So so a little bit of upfront thought to acoustics doesn't hurt. Any of those video tapes that I played, especially for the virtual people that may not be able to hear them through the conference software. There's on that channel at that address, you can pull them up and play them. So, and that's all I have unless somebody has some questions.
Anyone have any questions for Mark?
Mark, thank you so much for a wonderful presentation. And my question to you is, when you have rooftop units facing a residential, what is the best way to abate the noise before it gets to the building?
Well, I mean, the first best way in all sound things is to have a quieter unit. So now that's not always possible, so reduce the source. Any kind of barrier that will direct that sound up instead of out. And a lot of that depends on the geometry of your project. And you have some, especially here in the city, you have some very challenging geometries, low roofs next to high-rise buildings with windows. You can't really pipe that sound out of that hole. It's really tough. But almost all air conditioning that we have some kind of heat rejection device that throws it into the air. So whether it be a cooling tower or rooftop units, you have that problem. But if it's just a linear, it's across the street, across the property line, screen walls can do a lot and it doesn't matter. I mean, they don't have to be foot thick screen walls because most of it's just about bouncing it up so that direct arrival doesn't come straight through. That will help a lot. A good acoustical engineer or a good engineer that I mean, all the calculations are in the ASHRAE handbook. You can go through and do it. If it's the first time you ever did it, it's a little bit probably intimidating. But a good acoustical engineer should be able to give you a good idea if the manufacturer can tell you the sound power coming out of that piece of equipment. But yeah, it can be a problem.
Thank you, Mark.
Yeah.
Thank you.
I seem to remember there used to be a measurement called zones, and I don't hear it or see it anymore. Can you just explain what that is and why it's not mentioned anymore?
Do you have Lowe's or Home Depot? If you go buy a residential toilet exhaust fan, it's rated in zones. So zones is a measurement of loudness. It kind of looks like that chart with the hearing. It's not something that's easily converted from decibels. But yeah, it's a measurement of loudness filtered by how somebody hears. It's kind of like the NC, pre-applied NC RC criteria. But no, you don't see it much. The only place I know I ever see it is in residential kitchen hoods and toilet exhaust fans. But you're right, it's a very old concept, and there are standards on how to measure them.
What is the most effective way to specify the sound criteria, NC, RC, or sound power?
Okay, the mic wasn't working, but I'm going to repeat the question. So he asked, what is the most effective way to specify sound criteria in a space, NC, RC? Don't use dBA if it's indoors. It really doesn't matter for NC and RC, and talking to acoustical consultants that I know, what most of them tell me is what they typically design with NC, and if they're going out on the job after the fact, they'll use RC as a diagnostic technique, trying to figure out whether it's high frequency or low frequency that's causing people to be objectionable. So they kind of know where to go work on, but you'll see most of them in NC criterias. But the really challenging thing from a consulting, are you a consulting engineer? A vendor? Well, okay, but from a consulting engineer, if you specify, I want this space to be 35 NC, who's responsible? You know, without an acoustic, if there's no acoustical engineer in the mix that said, hey, if you put this equipment on it at this power and you do these things, you'll have 35 in here, then is it the equipment manufacturer? I know as an equipment vendor, I usually say, well, was it louder than I told you it was? You know, which is kind of a cop out, but I mean, that's all I got. I don't know what your application is. And the contractor says, well, I don't know how loud it was. I put the duct in like the engineer Drew told me to do it. And so sound criteria is hard to specify. You know, if it's a sound critical space, then it's always good to get a professional in there to actually do the calculations. But that also constrains the bid process because you have to have equipment. Then you end up with a sound power criteria. You know, you can be no louder than this in these octave bands kind of thing, which is kind of where that goes. But yeah, it's tough and it's hard to enforce.
We're time for one more question.
Okay.
Okay, so I ran into an issue recently. I'm also a vendor where another piece of equipment, same, I guess like similar but a different manufacturer, measured the sound power at a different location and distance from the specific unit. How do I compare the power of one versus the other when they perform the same, but their sound powers were different?
Okay, so they measured the sound pressure at a different distance.
Oh, yes, sorry.
Because power would be back. And there is a formula in the ASHRAE handbook. You can back calculate pressure to power in it's a hemispherical free field. So assuming it was an outdoor piece of equipment.
Yeah.
That's usually what you see. And there's a HRI standard. I may get this wrong. I think it's 370 that talks about measuring pressure at a distance and calculating power. Yeah, it's pretty common, but there is a way to, it basically assumes that the object is sitting in the middle of a big parking lot. So it's reflective within, I think, 15 meters all the way around it. And it's radiating as a 1/r² relationship, and therefore there's a calculation that you can do that, Ball's logarithms, that you can calculate back to the power or apply it at a different distance.
Okay, second question, sorry, really quick.
Sure.
So from an engineer's standpoint, when they're looking, it was a sound critical like library project, already had issues with sound like previously, so the engineer was being very—
Everybody's sensitive, right?
Yeah, super sensitive. So from, I guess, their standpoint, if they have a maximum sound criteria and are like someone's product data or, you know, published information isn't up to that standard, but someone else's is, how does that calculation play with legalities of it? You know what I mean? So there's measured sound and then there's like on paper sound.
Well, yeah, there's not, data's hard to come by. It's hard to measure on some of that stuff. There's, depending on, a lot of manufacturers have very variable capabilities of being able to do that. So that's a really good question. I don't know. I know the answer to that.
One more thank you for Mark and for his presentation. Yeah. We'll pass it off to Arturius.
Thank you, Mark.
All right.
We very much
Thank
appreciate
you.
it.
I appreciate you guys having me.
Yeah, no, I'll grab my question once we wrap up
Okay.
before you leave. Two quick announcements for the past. Okay, better? All right. Two quick announcements. For the past presidents that are still here, please see Kim. She'd like to get a group picture with everyone before you guys leave. Oh, you already got it? Oh, never mind. Okay, so action item done. And item number 2, the YA happy hour is happening. Please see Luke if you're still here. Oh, Luke, So he is your guide, and the first 2 rounds are on us, and he will be able to take care of that for you guys. It's at Peter Luger's, so if you go right outside and make a Peter Dillon's, damn. Peters, they got me. It's at Peter Dillon's. You go right outside, you bang a left, it's down 1 block on the right side. So thank you all for coming, appreciate it. And hopefully we'll see you guys all in September again. Have a good night.